Hello, everyone. This is the lecture for section 4.1, the basics of differential equations. So this chapter, this whole entire section and chapter 4, uh, deal with a very big part of mathematics. That part of mathematics, it's got its own, it's its own field within the mathematics that we know. It is called differential equations. Okay, so let me explain a couple things before we jump into what the heck differential equations are, first of all. Okay, so if you remember, right, in Calc 1, all of Calc 1 dealt with the derivative, the rate of change, right? Okay, and now that we're in Calc 2, right, nearly the entire time that you've been in Calc 2, we've dealt with the integral, the area under the curve, right? Okay. Um, Between Calc 1 and Calc 2, in that transition from Calc 1 to Calc 2, right, we had fundamental theorems of calculus, right? In particular, one of them stated, I believe it was the first fundamental theorem of calculus, states that uh, the derivative and the integral or the antiderivative are opposites of each other. They're opposite sort of operations, really close to opposites operations, right? The thing that was different was because when you take the derivative of a constant term, it's automatically zero. You can't get that constant term back. You actually have to do a little bit of fidgeting, which is what we're going to cover today, to get that constant back. Okay? So we sort of know that if we have a function and we have its derivative, right? In order to get the function back, we take the integral, we take the antiderivative. We won't get the entire thing back, but we get something close to it, right? Okay. But now let's go ahead and try to apply that to our physical world. Okay. In our physical world, what ends up happening is the latter thing. Okay, where we might know a rate of change of something. We might know how something is increasing or decreasing, right? We know that information, but we don't know what the equation that came before it is at all. So what I'm saying here is this, that we might have a method. We might have something that tells us where we can measure the change of something. We can measure f prime, right? But we don't know what f of x is. So if we can observe something changing, right? AKA if we can observe something, if we can observe the rate of change of something, can we get the original thing? Can we get the original thing back? Okay. This in and of itself is the impetus for differential equations. Okay. So that's the explanation, at least to sort of orient us, to get us started with all this, right? So now let me go ahead and get into defining what a differential equation is. Okay. A differential equation, okay, is an equation, right, that involves an unknown function f of x. We have no idea what f of x is, right? But we can write this differential equation, right, that contains this f of x and one or more of its derivatives. Okay, it can be the first, second, third, fourth, fifth, whatever. Okay, okay. A solution to the differential equation, okay, is a function f of x, is a particular function, okay, or let me not say particular, it's a specific function f of x, right, that satisfies the differential equation when f of x and its derivatives are substituted into the equation. Basically saying, right, that if we grab our f of x, whatever it is, right, and we start taking derivatives of them, and we put them back into our differential equation, then everything comes out to be a true statement. That is it. Okay? Okay. There are some famous ones. These are all very, very famous differential equations right here. Okay? The easiest one of them all is this one down here, the bottom right, the heat equation. Okay? It's Newton's heat equation. Okay? All of these equations are mixes of a function, right, and its derivatives into an equation of some sort that relates something to something else. It relates a function to different rates of change for that function. Okay? Okay. What we're going to do for this entire chapter is at least study one of the more basic type of differential equations. And it's not anything that you haven't seen before already. Actually, we can already do a lot of the work that you were about to see. Okay? So let me go ahead and start defining some stuff for differential equations themselves. Right? Now let's get into the nitty-gritty. Okay? The order of a differential equation is the highest of any derivatives that you see in the differential equation itself. Okay, so to give you guys an idea, okay, let's say I had this differential equation, okay, and I want to do two things. I want to show that this differential equation, well, first of all, find the order of the differential equation, right? And then I give you two functions here. I give you this one, right? And I give you this one. I am saying both of these satisfy the differential equation. Both of these are solutions to the differential equation. Okay? Both of these are solutions to the differential equation. Okay? Prove it. Show me. Okay? So first of all, let me do the very first bit. What is the order of the differential equation? If you take a look, this thing right there, okay, you see how it's d squared y or over dx squared? That is the second derivative. That is the second derivative, right? So, and that means, come on, there we go. That means this is a second differential equation. So this is a second order differential equation. I'm saying that these two functions, the blue one and the pink one, are solutions to our second order differential equation. Now I got to get to show you how to prove that these are solutions, okay? So the first one I'm going to do is blue. I'm going to do the blue one first, okay? So y is equal to 2, e to 2x. Y prime, hopefully you guys remember your chain rule, right? 2e to the 2x. Y double prime is equal to 4e to the 2x, okay? This is all we need. We need, if you guys take a look, right? I need the second derivative and the original, okay? I need just the second derivative and the original. So I get to plug them back into the differential equation itself and see what produce, right? What gets produced there. So it's going to be, I'm going to write this again, d squared y over dx squared minus 4y. This is my second derivative, so that's going to be 4e to the 2x minus 4 times the original, e to the 2x is equal to, and if you take a look, right, this and this are negatives of each other, right, opposite. So it's plus 4 minus 4. Both of those cancel. We get left with 0. Exactly what I expect it to be. Okay? All right. Let's do pink now, right? Pink one. Bam, bam. Okay? Y is our original. E to the minus 2x this time, right? Come on, x. Y prime. Minus 2e to the 2x. Y double prime. Positive 4e to the 2x. Okay? Again, I'm going to plug it straight into here, into the differential equation, right? D squared y over dx squared minus 4y. 4 e, and I forgot a minus 2x on all of these, so minus 2x, okay, minus 4 times the original, e to the minus 2x, right? Again, hopefully you guys see this, right? That's a positive 4, that's a negative 4 of the same amount, equal to 0. Exactly what the differential equation tells me it's supposed to be equal to, right? So I just showed, right, that both the blue and the pink highlighted functions, right, are functions that are solutions to our differential equation. Okay, I want to note something else really quick before I move on, okay, that both of these functions, both the y functions that I provide right there, right, those are two distinct functions. They are two different functions. Okay? All right. So now I want to bring up something pretty cool. Okay? Let me move down to the next example. Okay? Notice how it's the same differential equation as the one from above. Okay? And now I'm just giving you one function. And look what I did. It is the addition of the two solutions up above. And I'm telling you, for this example, right, that the function f of x also satisfies the differential equation. So let's go ahead and run the, let's run this through really quick, right? Let me put this in the middle. There we go. Y prime, derivative of this, right, is going to be 2e to x plus, and it's not going to be plus anymore, right? It's going to be minus 2e to the minus 2x, y double prime, 4e to the 2x plus 4e to the minus 2x. Hopefully you guys got your chain rules right, okay? Hopefully everybody sees that that's the derivative, right? Okay, let's go ahead and plug it into d squared y over dx squared minus 4y. My second derivative, 4e to x plus 4e to the minus 2x. That is the second derivative, right? Minus 4 times my original, okay, times my original, e to x plus e to the minus 2x, right? I am going to, in this first one, I get to factor out a 4. You guys see that? Because everything's got a 4 in it. 4 e to x plus e minus 2x minus 4e to x plus e to the minus 2x. It's happening again, right? So there's a positive 4, negative 4. Well, this cancels out to 0. Just like it says over here. Okay? Now, this is the cool thing that I wanted to show you. In the previous example, right, I said they were two different differential equations, right? These are two different differential equations, or sorry, they're two different functions, okay, that satisfy the same differential equation. And for this example, all I did is I grabbed both of those solutions and added them together, and I produced a different, an entirely different function that also satisfies the differential equation. It turns out this is a pretty big result once you get up to differential equations, that if you have two distinct solutions to a differential equation, then the sum of the solutions is also a solution. Whoa. Okay? Actually, it's the sum or difference. Okay? Cool stuff, huh? Okay, we're getting a little used to what differential equations are for right now. I know this looks very abstract for now, okay? But we need to learn how to sort of play around with them first before I start showing you real good applications and how to solve these things, okay? So what comes up next is a quick check. Like I said, um, I will provide everybody with some time to do these in class, okay? So don't fret if these don't make any sense for now, okay? Okay, I want to move on to general solutions, particular solutions, and initial value problems, okay? Here's where that nasty idea of a constant, okay, comes up, okay? Remember back in Calc 1, right? When you take the derivative of a constant value, it automatically becomes 0, right? And then when you take the integral of that function, right, you always had to do this plus c at the end, right? And the reason why is because if there was a constant back there, right, if there was a -5 at the end of the function that you were playing around with, right, and you took the antiderivative, right, you never got that 5 that was at the end of the equation back. You never were able to get it. The only way you were able to get it back is if you had a value of some sort, okay, that you knew it satisfied, okay? So that's what I'm going to cover in this instance right here. So, for example, okay, here's my function, okay? That is my f of x, okay? Whoa. And what I'm saying is it is a solution to this differential equation right here. And you see it, right? This is an x times y right there, okay? Now notice I say the c is any constant value. It can be whatever you want, okay? I'm going to prove to everybody, okay, that this f of x satisfies the differential equation. So this works out exactly how you think it does, okay? I only need, in this case, I only need the first derivative. Thank goodness, right? So if y is c over the square root of x squared plus 9, I can rewrite this as c times x squared plus 9 to the negative 1/2, right? Which means y prime is going to be c times negative 1/2 x squared plus 9. I got to do the -1 here, so it's going to be -3/2, right? Times the derivative of the inside, 2x. Okay? Some of this stuff cancels, so if you take a look, there's a 1/2 and there's a 2. Those go away. There's still a negative there, right? So this can clean up to negative cx x squared plus 9 to the negative 3/2. Got it? Okay. Now I'm going to show that it actually satisfies my differential equation. Okay. Here we go. So then x squared plus 9 times my first derivative, which is what we just found, minus c x squared plus 9 to the negative 3/2, okay, plus x times my original function. And I'm going to use the second rewrite, c x squared plus 9 to the negative 1/2. Okay? This, hopefully, has got to be equal to 0. So this is what we're trying to show here. Okay? I haven't shown you anything yet, but I'm going to clean this up a little bit, and we're going to see what this all sort of amounts to. Okay? What we have here is this, right? I'm going to grab, it's going to be minus cx times x squared plus 9 times x squared plus 9 to the negative 3/2. I'm just rearranging the furniture, really. Cx x squared plus 9 to the negative 1/2. Okay? This is the bit that we need to clean up a little bit. Okay, if you notice, the power here is to the 1 power, right? I don't need it to the 1 power. Whoa. What was there? Cx, there we go. I need this to be, let's do 2 over 2. Yeah? Okay. The bases are the same, and I'm multiplying. That means I can add the exponents. So minus 2 over 2, or sorry, 2 over 2 minus 3 over 2. That leaves us with negative 1 over 2, right? So all of this cleans up to minus cx x squared plus 9 to the minus 1 half plus cx x squared plus 9 to the minus 1 half. And we have this thing happening again, right? So notice that both of these, this and this, are opposites of each other. One's negative, one's positive. So this is actually 0, exactly how I wanted it to be from the differential equation. Cool stuff, huh? So now what I want to point out is this, is the fact that this was the function that I was referring to, right? This is the function that I said was the solution to this differential equation, right? It didn't matter what my c was. I just said that it was a constant value, right? So what does that mean? All of these, every single one of these 4, at least that are written right here, and many more. It is not limited to just these 4, okay? That c value, like I said before, that c value could be whatever it wanted to be, right? Each and every one of these, each and every one of those f of x's with a different c, right, is a solution to my differential equation. Okay? So the question now becomes, right, well, I want a particular. No, remember how I said I didn't want to use the word particular solution, because that's that's actually the terminology, okay? Let's say I wanted to pick out one particular solution out of all of the collection of the f of x's that satisfy this differential equation. So what do I do, right? How do we do that, okay? If we have a particular point, if we have a particular x and y, so remember, let me go back. My function, right, my f of x, was c divided by the square root, right, x squared plus 9. Okay, I'm going to change this around. I'm going to grab that f of x, and I'm going to change it into y. Okay, so notice what we have here. Okay, if you gave me an x and a y value, right, then my c value is completely determined. I can solve out for a c value, right? What that means is if I wanted a particular one of these many curves, okay, if I wanted a particular one of these many curves, if I had an x and a y value that I needed to satisfy, I can find my c, okay? That is the difference between what we call a general solution, okay, and a particular solution. That's the terminology that I was trying to avoid using before, okay? A general solution, let me scroll down a little bit, okay? A general solution to a differential equation is the family of functions, okay? And we tend to write it this way, like a script F, and it's a collection. It's a big, huge, long list of functions that are solutions to the differential equation, okay? What I'm saying here is my general solution for this, right, is going to be this. It's going to be y is equal to 3 over, whoops, sorry, the other way around. Look at me go. Come on. C x squared plus 9. This collection of functions, right, is my family of functions. These are general solutions to my differential equation. Okay? The second you choose one particular function within this family of functions, you have a particular solution. Okay? So a particular solution, right? A particular solution to a differential equation is one specific function, an f star, that's in here. It's one particular function that's in here that is a solution to the differential equation. So this is y is equal to -3 over x squared plus 9. Since this one has everything defined, you see that? It is particular. It is part of that family. Got it? Awesome. Okay. So now, this is the thing, this right here. Particular and general solutions are the things that mathematicians, particularly that study differential equations, these are the things that they're mostly concerned with, either finding a general solution or finding a particular solution to a differential equation. Okay, and how do you do that? Okay, we already covered how to do that. So long as we have a particular point, we can determine that C value explicitly by solving it out because we have an X and a Y. Okay, so for example, right, find the particular solution to the following initial value problem. We have this equation already, right? We have a solution. We have the general solution for them, right? So our F collection, right, is going to be all the functions C, and let me write it correctly, are these. F of x is equal to C divided by x squared plus 9. These are our general solutions, right? Got it? Okay. This one has a particular stipulation, though. It's given us a specific point. It's saying that if we plug in 0 to f of x, right, our y value is going to be 2. So the point that we are trying to satisfy here is this, right? 0, 2. We know what the general solutions look like, right? And just like I said before, since we have an x and a y, we can flat out solve for a c, right? So this is telling us, right, that 2 has got to be equal to c divided by, and let me make the square root, 0 squared plus 9. Hopefully you guys see that. My y value's got to be 2, my x value's got to be 0. At this point, I can just solve out my c value, right? So this is going to be 2 is equal to c over, what is that going to be? The square root of 9, right? 2 is going to be equal to c over 3. C is equal to 6. So then that means particular solution. F of x. And I'm going to use the notation that I have up above. It's going to be a particular f star. Is equal to 6 over the square root of x squared plus 9. This is a particular solution. Okay? This is the particular solution that's running through this point. Okay? Now, before we move on, okay, we come back up here, right? What we just found was basically this exact curve. We found the curve that does this because we wanted to go through here. You guys see that? And then come back down. We found, maybe I should do it in space pen and maybe not too thick. There we go. We found this solution. We found my space pen solution. The one that goes through 0, 2. And not what I wanted to do. There we go. Whoosh. Okay, we ended up finding that one in particular. Okay, so out of the entire collection of equations that can satisfy this differential equation, we picked out one, a very specific one, the one that goes through 0, 2. Okay, so like I said, we're still just getting used to what a differential equation is, right? I'm showing you, really showing the like very basic of what a differential equation is, how do we work with it, the difference between general and particular solutions, okay? We'll work on these in the next couple sections. What comes up next is a quick check. I've got a couple differential equations here. It's differential equations that, from up above, I'm asking you to find particular, okay? And I believe that is it. What comes next is lecture questions. Okay? Awesome. If there's any questions to the stuff that we just covered, ask me during our quick check times. Come downstairs to the tutoring center or come find me at my office. Best times to really ask me for stuff, okay? Besides that, happy studying.